So, hi, my name is Will Morgan. I'm the Director of Engineering at Foursquare, and we are a data company. What we sell are licenses to access various location data sets. We maintain a database of over 100 million places, which are businesses, points of interest, and so forth, in 190 countries, along with downstream data assets like visitor reports, marketing resources, that sort of thing. We expose APIs to our customers to permit them to activate new feeds, and internally, it's all stitched together with microservices. So, in terms of market position, Foursquare is somewhere between a product and a platform. I've been working here for about 8 years, and I want to share some thoughts about how we think about limits in a microservice architecture. So, throughout this talk, when I use the word limit, this is what I'm talking about: quotas, constraints, setting bounds on different bits of resources, how quickly things can happen, how much compute you can use, and things like that. If you take nothing else from this talk, take this. No matter what our code says, no matter what the product documentation says, our software always has limits. You can choose to declare, monitor, and enforce those limits or not, but the limits don't go away if you ignore them. But if you design your limits in a proactive way, all sorts of good things happen. Here are the things we'll be talking about. But I want to take a step back to introduce this whole concept, to take a step way back to the early days of programming. In these trying times, I like to seek out wisdom from the early days. This is a photo of Edgar Dijkstra, who worked as a programmer and program manager in the 60s and 70s before he moved to a teaching position at UT Austin. A Turing Award winner, visionary programmer, and fortunately for us, prolific writer. He was blogging before blogging existed. Short articles on paper, often handwritten, often kind of arrogant vibes. I get the feeling that he would have loved Twitter, except for another trait that he shared with many great programmers, which is that although he loved software, he was deeply distrustful of actual computers. They say he never owned one, though he lived to 2002. Perhaps his most famous contribution to the field was an article he wrote called "Go To Considered Harmful," which spawned 100 different articles about different things considered harmful. But Dijkstra basically said never use GoTo. And there was this huge debate throughout the 60s and 70s where everybody was wrong. And Dijkstra was right. And in the end, he won the argument so exhaustively that when they designed the Java language, they were so afraid of angering him that you're not even allowed to name a variable GoTo. You can try it. It's a syntax error. So you can try to do this. Anyway, I want to talk about an article he wrote in 1982 comparing hardware and software. And the title is "Why is Software So Expensive?" This is what he wrote about the comparison. You can read it for yourself. But at a high level, he's saying that that hardware is trying to solve a different problem than software because hardware needs to work within certain tolerances, and that hardware has this sort of statistical property of correctness where small changes within expected variation are more or less guaranteed to still give you useful results. And it's not just hardware that has this property. When you look around, you have to see many things have this property of you can change things a little bit and it's still okay. So if I'm listening to a song on the radio, I might, if the radio is a little bit broken, I can still enjoy the song, or I can scramble up some English prose. Maybe it might look like something like this. And this has been pretty well mangled, but most readers can tell at a glance what it's saying. But Dijkstra says software is different, and he's got a proof of this, but what it boils down to is that every useful program is a nonlinear system, and all nonlinear systems have some bits that really matter, that really affect the output. And this touches on a broader point, which is that to Dijkstra, the craft of programming was at its heart a mathematical endeavor. He believed that a program was a proof, and the programmer's job was to prove that the program generated the correct output. This especially impacted the way he felt that computer science should be taught, which is as a branch of mathematics. In the opposing view, programming is a scientific field, which is that you state a hypothesis about the program's behavior and then run tests to disprove that hypothesis. And if enough of those tests fail to disprove your hypothesis, then what you have is a theory of the program's behavior, and that's something valuable. So in a sense, this is a philosophical debate. And if you were a working programmer in the 80s and 90s, you might have followed it with kind of a detached curiosity. When a tree falls in the forest, does it make a sound? Who can say, after all, whether programming is really a branch of mathematics or science? I can, because although Dijkstra was a visionary, he was wrong about this. MIT agreed, and in 2008, they switched their Intro to CS course from Scheme, with the textbook on the left, where you compose closures in a lambda calculus, to Python, textbook on the right, where you write a program to control robots. And for the past 15 years, nobody has seriously questioned the primacy of scientific exploration over first principles reasoning for the effective teaching and execution of software development practices. It's no coincidence that in those same 15 years, we've seen complete abandonment of waterfall methodologies for agile methodologies, where above all, the focus is on shipping something, anything, within the first few weeks of the project. I'm a hiring manager. One of my responsibilities is to talk to a lot of candidates, and it's incredible how pervasive the 2-week sprint and agile methodologies are. Even companies that are, you might think they're conservative, they're stodgy. Everybody's doing agile now. And yet, when we design our products, have we really taken these lessons to heart? I want to give a worked example from the product world. So, how many times have we seen a variation on this conversation? So here we have our revenue organization represented by Kelly, and she's asking a question about the behavior of the product. And Dwight's over here in the product organization, maybe he's an engineer, maybe he's a product manager. He avoids the question by telling her that there is no limit. So Kelly goes back to the customer and tells them to start submitting their requests. We all know where this is going. So now we have an outage, an unhappy customer, unclear communication, a situation that has to be resolved. And I'd also like to address what's happening to the social organization of a company that encounters this situation again and again. If Kelly is good at her job, what she's going to start doing is keeping records of the kinds of requests that succeeded and failed and train up new people in her org with tips and tricks for getting the system to work. So they're going to develop idiosyncratic little superstitions and rules of thumb, which are not only going to be invisible to the product org, which is bad, but there's also going to be a lot of variation between the teams. And all this is because product didn't have well-defined limits on its safe operation. In a microservices world, this applies not only at the product customer boundary, but within engineering teams. So we're all Kelly now. Because all software teams are mediated by these microservices. And everybody's going to fall into this pathology unless we get real about limits. So Dwight's title might be software engineer, but he's not really doing engineering, is he? What would it look like if we built bridges this way? Calvin and Hobbes would be the answer. It's a ridiculous concept, and yet far too often, this is how we think about limits on our software. So you might ask me, how many requests per second can I submit? Now I'll tell you, I don't know, hit the server, and if you knock it over, don't do that again. So product thinks that they're all like Bradley Cooper here, but really they're more like this bird. This is an ostrich, and what it's doing is rotating the eggs in its nest to ensure that the heat's evenly distributed. It used to be thought that the ostrich was trying to hide, reasoning that if I can't see the danger, it doesn't exist. Well, that's a myth. Ostriches don't do that, but people definitely do. However, the limits don't go away just because you pretend they don't exist. Rush said it best in a song called Free Will. If you choose not to decide, you still have made a choice. So that's my first point here, which is that you have to know your limits because you don't have a choice. Those won't go away. Organizations learn this lesson at different speeds depending on how quickly they respond to the pain of missing limits. In particular, a platform company is going to learn this lesson very early on because otherwise it's going to get buried in the long tail of unreasonable requests. So if you're attending this talk and you work at a platform company, I'm telling you what you already know. Product companies, on the other hand, can coast for a very long time with ill-defined limits because of the sales cycle, and you can make a lot of money selling to a customer base where you're basically subsidizing the long tail. But if you're at a product company who wants to become a platform company, you're going to feel this pain again and again and again until you learn how to run in the metaphor. But defining good limits isn't just about avoiding pain. There's a lot of follow-on benefits that I want to talk about. So let's talk about the good things that happen when you're proactive with setting limits. Let's talk about bugs. So I picked the cutest picture of bugs I could find because nobody likes to talk about bugs. There have been bugs that have killed people or destroyed spacecrafts, bugs that have lost a lot of money in the stock market. This bug that I want to talk about isn't any of those. It's just old. It's probably the most long-lived bug in the book. This is a binary search on a sorted array, and it's written in Java, but you can find this bug in any language. You can find this algorithm more or less verbatim in any number of textbooks, programming guides, standard libraries from the years 1945 to 2006. And what's unique about this bug is that one of the first things we ask a computer science student to do after we show them the algorithm is we ask them to prove it correct. So it's a bug that's been, it's been proven that it doesn't exist more than any other bug. So the bug's on line 6 here. And the problem is that if the array is very large and the value we're searching for is in the upper parts of the array, low and high are both in, so the result of adding them together can overflow. And here's the corrected code. So when calculating mid, you take the difference between high and low and you halve that. It's equivalent mathematically, but it can't generate an overflow. And now we know it's correct. It only took 50 years. Usually, when people tell you about this bug, there's a sort of cynical moral attached, which is that the goal of bug-free programs is so beyond the capacity of human intellect as to be functionally impossible. If we can't reliably find bugs in textbook algorithms that have been proven correct over the course of decades, what hope do we have to build software that's safe or secure? And that's an important moral to keep in mind, but I want to draw a different lesson, which is that by refusing to declare and check limits on their input, that limit didn't go away, it was just hidden from the API. So let me demonstrate with a different fix for this bug. So I argue that this also fixes the bug. Not only that, this also fixes every bug, which we're not aware of, if that bug only affects arrays of size greater than 1,000. Furthermore, you don't have to know anything about integer overflow to ship correct code like this. The correctness flows from the well-defined limit. Now, nobody is selling binary search as a service. This is a metaphor for a product, and your product might have certain limits. So while you might say, "Hey, listen, I have an array to search, and it's larger than 1,000. What am I supposed to do?" There are plenty of products where the input is less than 1,000, and you can have a great, well-defined, profitable product setting limits like that. So it's a little bit contrived. But what I want to convey here is that by introducing this limit, we've changed the way we think about the program from something that will fail in new and unanticipated contexts to something that needs to work within well-defined tolerances. So if you know your limits, you will protect against bugs that you can't see. And I want to go back to this from my next point, which is that this code still has the overflow bug. But I would say that we are very likely to detect it before it makes it into production. Why? Because if you put limits front and center in your service interface, it gives you an obvious way to test the new behavior. So you write your user story, I want to do binary searches on arrays of sizes up to 10,000, 10 million, whatever it is. And the engineer changing the code says, okay, well, I need to test it. So what do I need to do? Make an array that is as big as the biggest one you're asking for, and make sure this program still gives me the right results. So even if that engineer doesn't know about integer overflow, they'll still encounter this behavior. And then, so now you're doing actual engineering. So future engineers will know how to test this stuff. There's one more thing I'd like to see in this code, which is I'd like to see a lower bound as well. And contrived example yet again. But if this is a product, well, how are we charging for the product? Maybe it's not profitable for us to offer a binary search to a customer on small arrays. Lower bounds matter a lot when personally identifying information is involved. So here's an article I read first in 2016, but it was floating around a bit longer than that. So this guy set himself up as an advertiser on Facebook and designed an ad campaign that was so hyper-targeted that it only matched one of Facebook's users, and that user was his roommate. And so he started sending him ads telling to wash the dishes or whatever. We all thought this was funny in the mid-2010s, but nobody thinks this is funny anymore. If I can show you an ad, I can make your browser fetch a pixel from my server. That means I get your IP address. People have been targeted for hacks using techniques like this. And the reason is that Facebook didn't have lower limits on their product. Why is this so hard? Limits are everywhere in the real world. And for the purposes of time, I needed to cut a little bit about why I think software is different just culturally here. But look around, you'll see limits everywhere. Notice also that the limit is useful to users even when they don't stick to it. So the speed limit sign. So the speed limit says 30. People might go 30 on that road. They might go 35. If they go 60, they know they're doing something very wrong. And this permits us to ramp up enforcement according to a sliding scale. What does that look like on our side from a product perspective? So here's an example of one of the products we have at Foursquare. These dots that you see are customer requests, and the y-axis is the size of the request. So there are 3 lines. The green line is the documented limit. This is what we tell our customers. You're permitted to submit a request of up to this size. The blue line is what the software enforces. So this is when they'll actually get an error. And then the red line somewhere up here is the true limit if it didn't exist. We don't know exactly where this is because we haven't tested it, but we know it's somewhere beyond the blue limit because we have. So you see here, everyone's staying within the green except there's one request over there where there's just a little bit above. And the presence of the limit first gives us something that's easy to observe, so it's improving our observability, but it also allows us to reason about how do we interact with this customer? Do we need to reach out to them, encourage them to upgrade their plan maybe? So these are numeric limits, but the same concept applies to capabilities as well. Less than 2 months ago, this vulnerability broke the internet. Did anyone else spend a weekend patching all their systems? Here's what the vulnerability looks like at a high level. So this is not the most inert code in the world. We're reading user input without sanitizing it, but it's pretty safe looking. And what is the actual problem? The problem is that depending on what the user input string looks like, the logging system can be convinced to make a network call. And depending on what that network call returns, it can execute code, and that's game over. So whenever these vulnerabilities come out, you get to read the opinions of a lot of different programmers explaining what they think went wrong, and especially why their particular way of doing programming would have avoided this situation in the first place. And those opinions are, you can skip a lot of them, but there was one article that was pretty great, preventing it with capabilities. And this author's point about the whole thing was that no programmer is going to expect that just because I'm passing a string into the logging system that it's going to make a network call. And he goes on and says, why does the logging system get to access the network at all? And he gives sort of his example. This is what he'd like to see in like a main entry point into a program. If you want the network, it has to get the network. It can't just do it by itself if you want to access the file system. So this is the example that he gives, and he says that working with capabilities is an improvement here. I'd go even further and say I want an interface like this. So I did a network migration a while back, and we moved an important service from one VPC to another. And then we found out that one of the microservices it was dependent on could no longer be reached, resulting in an outage. And I called up the network guys. We fixed it pretty quickly, but afterwards they said, you need to give us a list of all the services that you depend on. And I said, I have no idea what services I need. Or I might have said something like, oh, I need everything. Just give me everything. And if you've done this sort of thing enough times, you grow to be very skeptical of the idea that the fix is documenting your dependencies, because the docs get out of date. But what if your network access was configured in this way? In this model, all network access is forbidden except what you allow specifically. So this example is in Java code. You could also do this at the level of container orchestration. And then when you do a migration, you just look it up. The code needs to be able to access these things. So know your limits. Migrations are less painful. So far we've been focusing a lot on the benefits to we ourselves as developers. I want to talk about the benefits to our users here. So my lesson is that the limits themselves are often better documentation than usage guides or technical overviews. So there's a lot of text, but it's from one of AWS's new products. This is from the user manual. I led Foursquare's integration with this product last year, which meant writing the spec, keeping the project plan, keeping the schedule, reviewing the code. And you see these limits are on pages 99 and 100. But when I trained up new engineers on the project and I told them there's this new thing called AWS Data Exchange and we need to integrate with it, and they asked me, what is AWS Data Exchange? This is the first thing that I showed them. And the reason is that if you look at the limits, you start to get a very good idea about what the product actually does. Right off the bat, you see a limit here, file size for assets imported from signed URL. Okay, so whatever the product does, it involves importing some assets that can be no bigger than 5 gigabytes. And then you scan down, number of assets that can be exported, 2,000. Okay, so there's a certain number of assets, they get exported in something called an export revisions job, and so forth. I'd also point out, look at all those powers of 10 that are in there. Programmers hate them, but users love them. It's you know that the true limits of these things are much higher than these, but it makes it the whole system very easy to understand. Fred Brooks had a quote, which he said basically, I don't want the high level documentation. I want to see the schemas. And I would say that my refinement to this is I want to see the constraints on the system that will help me to understand what it's doing. So not just for your users, more useful documentation. More useful documentation for your users, but it's also going to be more useful documentation for you. So here's another worked example here from a Foursquare product that we have. So I operate a data pipeline. Users are allowed to submit requests into it. We generate data for them. And there's a certain rate limit on that. There's a maximum size that each deliverable can have, and then we retain it for a certain period of time for the users. You could give these 3 statements to a 10th grade math class, and half the students would know the question before you even asked it, which is, how much storage do you need to support these limits? And the answer is 85 terabytes, followed by multiplication. So first things first, do you have 85 terabytes per user? If you don't, then something has got to give. We know that these aren't the real limits. And so this means that anyone that is, internally, they're reviewing the docs, they can look at this. They don't need to be a programmer on here. They can just say, hey, wait a minute. I see, this is how much network we're going to need and how much processing power. Where's the disk space coming from? So knowing your limits, you'll be able to see new limits that you didn't even know that you have. So these are the good things that will happen if you're proactive. If you're proactive about setting limits. If this is interesting to you and you wanna work with software with well-defined limits, then I want to work with you. We're hiring for data engineering. We're hiring for data science. We're hiring software engineering positions, and please reach out. And that's it. Thank you.